So we take a look at this, just remind ourselves that we're not able to take the square root of negatives. When we're taking the square root, we're asking what number times itself makes what's underneath. The square root meaning what times itself makes this. Well, let's hypothesize that x is positive. Well, if x is positive, when we multiply it times itself, a positive times positive is positive, so that's not going to work. Well, what if x is negative? If x is negative, a negative times itself is positive, that's not going to work either. And of course, 0 times itself is 0. So we're not going to be able to multiply any number times itself and get a negative. So there is no real solution to this. So we simplify it in terms of imaginaries, where by definition we call the square root of negative 1 I. So remember, if we have a number or something underneath here, we can write that, call that negative 1. And that that allows us to take the square root of these separately. So the square root of negative 1 is I, and then we need to evaluate the square root of 28. Well, 28 is not a perfect square, but it is 4 times 7. So we can take the square root of 4 and get 2. 7 is not a perfect square, so it stays under the radical. And that's typically the order we write it in. If there's a number out front, it goes in the very front, followed by our I, followed by our radical. So that's simplifying a square root of a negative. So after we do that, then we start adding and subtracting real numbers and imaginary, where we consider something of this format a complex number. Complex because it's both real and imaginary. And in terms of complex numbers, this is the standard form of writing that. So here we have what kind of looks like adding two polynomials, but our polynomial is actually a real number and an imaginary number, simply combining like terms. 3 and 7 are both real numbers, 8i and minus 5i are both imaginary. So if we combine the real, we get 10. If we combine the imaginaries, we get minus 13i. So that's in complex form, real and then the imaginary part. Here's another one that we can do, and we need to simplify our radicals first and then see if we have any like terms. Writing all the steps that we did on the first problem of breaking that apart in terms of negative 1 times 64. If we have a square root of it, we know that's going to be a positive value. So the square root of a negative, that's going to be imaginary, and then what's the square root of the real part? The square root of 49 is 7, so that's 7i. And if we combine what's alike, we have 13 real numbers, or our real numbers total 13, and then the imaginaries total 15i. But we had to get it into I notation in order to combine those. Now, if we take a look at this one is easy to mess up. It's easy to want to go ahead and multiply these together first. And if they were both real numbers, that would be fine. But it turns out if we multiply those together first, we end up with the wrong sign when we simplify our answer. These are both imaginary. So for the first one, it's imaginary. For the second one, it's imaginary, and the square root of 25 is 5. So if we multiply these together, we have 3 times I times 5 times I. 3 times 5 is 15. I times I is I to the second. Now we said that I, by definition, is the square root of -1. So what does that make I squared? Well, if we want to find I squared, we square both sides. So I squared, the square root and the square cancel. So I squared is -1. So anytime we have an I squared, we're going to replace I squared with -1. So 15 minus -1 is. So we multiplied on the previous one, so now we're multiplying except instead of two things together, we have a binomial times a binomial. So 7 times 8 is 56, and that's times I. And then we distribute the 9I. So 9I times 5, 9 times 5 is 45, and that's times I. And when we distribute to here, 9 times 8 is 72, and I times I is I squared. So that's 9I times 8I. So 9 times 8 and I times I. So the middle two terms are alike. Those are both i's. If we add 56 plus 45, we get 101. I squared is -1. So this is 72 times I squared, or 72 times -1, which makes that minus 72. And then we just combine like terms. So those are alike. Those are both real numbers. So they have different signs. So we subtract them. That would give us 37. Take the sign of the larger. And then we have 101 as our imaginary part. So when we have it completely simplified, we have a real and an imaginary part. Now, it is possible for one of those parts to be 0. If we have a number that's purely a real number, then in complex form, it has no imaginaries. If we have a number that's just imaginary, then it has no reals. But if it's both real and imaginary, then neither one of those are 0. So this would be standard complex form for all three of those numbers. Even though the first one is just a real number, the second one is just imaginary. Now, when we divide by a complex number or an imaginary number, it's a little bit different. What we end up doing is multiplying by the conjugate. And what we mean by the conjugate is that we keep the same term before and then how we just change the sign in the middle. And in a moment, we'll see why we do that or what's going to happen. So I would not worry about multiplying the top out yet. So on top, we have 3 times 4 plus 9i. And when we distribute the bottom, we get 4 times 9i. So 4 times 9 is 36. When we distribute the minus 9i, we have a negative times a positive. 9 times 4 is still 36. And then when we multiply these together, we have a negative times a positive, which is negative. 9 times 9 is 81. And I times I is I to the second. So on top, we're just going to leave that. On bottom, notice the middle two terms are opposite. So 36i minus 36i cancels. I squared makes a negative 1, so this is really negative 81 times negative 1, which is plus 81. So 16 plus 81 is 97. Now that doesn't reduce. One of the main reasons I didn't multiply that out was to see if it reduced. And remember, when we reduce, we want things that are factored. So if we left that as a product, it's factored, but there's not a common factor here. So we could multiply that out, or we could leave it like it is. Now, the last thing that we're going to look at in this section is raising I to larger powers. We've said that by definition, I is the square root of negative 1, and I squared makes negative 1. If we multiplied this by another I, if we had I squared and we wanted to find I cubed, we could multiply both sides by an I. So I cubed is negative 1 times I, or minus I. If we wanted I to the fourth, we would need to multiply that times another I. So that would give us I to the fourth. I times I is I to the second, and then we put a negative out front. Well, I to the second is negative 1. Minus a negative makes a positive. So that's just 1. And then if we did I to the fifth, it would be this, both sides times I, so 1 times I would be I. If we did I to the sixth, we'd multiply both sides here by I, and that would give us I squared, which is negative 1. And we would fall into this pattern. Every fourth time we would repeat. I, negative 1, negative I, 1. I, negative 1, negative I, 1. But we don't want to do that all the way up to 31. If we go all the way up to 31, then that's going to take a while. But we can utilize the fact that we know what I squared is. I squared is negative 1. So let's rewrite I to the 31st. So many I squareds, and then if we have 1 left over, then times another I. So if we have 31 factors of I times 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 I, all the way to 31, let's see how many pairs we can make. If we divide that by 2, we get 15. And we have 1 left over. So look what we can do. If we raise that to the 15th power, when we have something with an exponent and that gets raised to an exponent, those are multiplied. So 2 times 15 is 30. We need 31, so we need 1 more I. Well, how does that benefit us? Squared, we said, is negative 1. When we have 1 to any power, 1 to any power is just 1. If we have an odd amount of negatives, negative 1 to the 15th means negative 1 times negative 1 times negative 1 until we have 15 of those together. If we have an even amount of negatives, that's a positive. But if we have an odd amount of negatives, that makes a negative. So an odd amount of negatives will make that negative. 1 to any power is 1. So this just simplifies to minus I. To minus I. Now let's do one more of those. If we want to rewrite or simplify I to the 43rd, we want to write that as I squared to some power, and then if we need another I. So if we have 43 I's, how many pairs can we make? So 2 goes into 4 twice. 2 goes into 3 once. So we can make 21 pairs with 1 left over. So we can put a 21 here, and then we have 1 more I here. Why 21 here? 2 times 21 is 42, and this makes 43. I to the second is negative 1. Negative 1 to an odd power is negative 1. So this just makes minus I.